Okay, so yeah, this is joint work with Dave Parker and Nick Hawes at the University of Birmingham, and this has been work that we have been doing in the context of the Strengths project, which is a EU project that has been looking into the deployment of mobile service robots into everyday environments for long periods of time. It finished a couple of months ago, but anyway, this is still work done in that context. So we have been doing a lot of planning in the context of this long-term autonomy of mobile robots in everyday environments, and we have generally typically looked at this kind of model for planning. So we have a mobile robot that can navigate between locations in a topological map. In certain locations, it can execute some actions, like retrieving a water bottle from the kitchen, asking someone if they want some water, searching for an object, this kind of thing. And because we are in human-populated environments, of course, we have quite a lot of uncertainty in terms of the outcome of actions, also because of course, of the robots actuators and stuff. But in particular, we have a lot of uncertainty in terms of navigation, in terms of duration of navigation actions, mainly because some of these areas are populated differently throughout the day. So you can imagine that around the kitchen area, at lunchtime, it would take a lot more time to go to navigate there than it would at 3 p.m., for example. So we basically are modeling this then as an MDP, which is slightly augmented to add a set of discrete distributions over the possible duration of our actions. So in this case, you can see if you execute action A1 in state S1 and move on to state S3, you have a probability 0.2 of taking 4.5 seconds and the probability 0.8 of taking 10 seconds. This can kind of be learned from data. You can run some clustering algorithms to try and figure out more or less how to define these discrete distributions. And then in Strands, we typically have two classes of tasks that we want our robot to fulfill. First, we have this more user-driven type of task, which we are really providing some value to the humans we are working with. And as an example that we'll be using throughout this talk, imagine that we have a robot that in the morning goes to certain offices, in this case office 6, 7, and 11, asks the person there if they want some water. If the person wants some water, the robot goes to the kitchen to pick it up and goes and deliver it. Okay, so given that this is something that we want to do, let's say in the morning when people are arriving to the office, we can say they want this to happen between 9:15 and 9:30. So we have also a deadline for when this task should be executed. In this case, we have a 15 minutes deadline. Well, this is our primary task, really, a user-driven task that we want our robot to fulfill. You can see that the specification in natural language is already slightly involved. So in order to cope with that, we are using the co-safe fragment of linear temporal logic to write down our specifications. And this is basically the fragment of linear temporal logic where for all infinite sequences that satisfy a formula, you can kind of break this infinite sequence into a finite prefix from which on you can do whatever you want and the formula will still be satisfied. This is what is known as a good prefix for the formula. So these tasks here, the specifications have a very well-defined notion of the task is completed, which allows us then to kind of do them within a deadline. A second class of tasks that we have also been looking at quite a lot was one of the main goals of Strands is really having these robots deployed for long periods of time. So we want robots that learn spatial temporal models of the environment and learn about different processes that are happening in the environment. An example I have here, let's say that our robot, in the end of the day, typically has to go around the offices, figure out where, look for scattered cups and move them to the kitchen. It would be nice if in the morning we already start looking around the offices to kind of update our models for cups location. And then in the afternoon when we go and do this cup retrieval task, our models are better so we can be more efficient on our planning. Our goal here then, since these are not really user-driven tasks, our goal here is to use our spare time to maintain and build these spatial temporal models of the environment. Okay, so on top of our MDP, we also have a soft goal reward. As you can see, typically these are observational actions that we are talking about for these soft goals. So we are more than fine using just a simple reward function that maps for a given state and action how much our learning component values that specific action to be executed at that state. So formalizing the problem statement, we basically have two objectives. First of all, we want to maximize the probability of achieving our co-safe task phi within the deadline. Second of all, we want to maximize the expected cumulative soft goal reward within that same deadline. Of course, we're giving priority to the first, but we want to kind of manage trade-offs between the two. First, let me show you how an optimal solution for this would look like. It's pretty straightforward, even though it's also pretty brute force. So the idea would be to encode the passage of time in your state representation. So looking here, in an original model, you just have the state of the environment. In your augmented model, you have the state of the robot in its environment, plus how much time has passed throughout execution. In this model, we can use known probabilistic model checking techniques to build what is called the Pareto front for these two objectives. In the Pareto front is basically a set of policies for which you cannot improve one objective without decreasing your performance on the other one. So they are what is known as Pareto optimal here. Just to give you a small diagram that describes what I just talked about. So we start with a model and a primary task. We add the timing information to the model, as I told you. We build an equivalent deterministic finite automaton that basically accepts the root prefixes of our co-safe LTL task. This is kind of standard stuff. We do the product of these two models to build what is known as a product MDP. In this case, it's kind of a product timed MDP. And then maximizing the probability of achieving your co-safe task within the deadline in this model boils down to just doing some reachability to maximize the probability of reaching a given set of states. So we can use, again, known techniques to generate the Pareto front for those specific two objectives. This is how we would solve it optimally, and this is how, for the example I showed you, how the Pareto fronts would look like for different deadlines. So a couple of things that I want to mention here. So you can see that in the Pareto front, we have these dots here which represent the deterministic policies of the Pareto front. Then we can kind of attain any value, any Pareto optimal value between two deterministic policies by doing a convex combination of them. Furthermore, we are more interested on this side of the Pareto front because this is the primary task. So we might be able to want to sacrifice some of our probability to achieve the primary task. But anyway, it is a priority, so we want to stay here. And why do we are willing to sacrifice some of this probability to achieve the maximum task? Because we can obtain quite a lot of increase. You can see here that by sacrificing a small amount of maximum probability of achieving phi, we can get a substantial increase in the expected soft goal reward. Given that typically these soft goal rewards are obtained from observational actions that are suggested by models of the environment. Our hypothesis here is that then in the future, by doing a small sacrifice of our primary task now, in the future we'll be better at doing our primary tasks because our models are more accurate. The final thing I want to say, of course, this kind of thing, as expected, blows up quite a lot. So for the small example I showed you, talking about millions of states, and to calculate these optimal Pareto fronts, it takes us, in the order of an hour, more or less. So we want to do better, and the proposed approach in this paper is kind of following a very common approach in the planning community, which is, okay, let's solve a problem relaxation first, and use a solution from that relaxed problem to make the solution of our the time-bound problem we want to solve easier. In this case, the relaxed problem we're looking at is, instead of maximizing the probability of achieving our task within the deadline, we are trying to minimize the expected time, the cumulative expected time to achieve the task. This is much easier to solve because, we don't really need to encode the passage of time in the state space anymore, so the models here are much smaller. And again, so if you look at this as a diagram, it's again pretty much standard stuff. These first two arrows are of the stop action you can ignore for the sake of the talk. It's just some technicalities that aren't very important. So in this case, what I want you to notice is that we are not adding a timing information here. So this product MDP is much smaller, and calculating the Pareto front for the expected time objectives can be done much quicker. And that's what I have here. So this is the Pareto front for this case, and you can see that now we have just a couple 100,000 states, and we can solve the problem in less than 10 minutes. Now, how do we use this to kind of guide our search for the time-bounded problem? We are going to prune our product MDP, taking into account this set of deterministic policies that we have calculated for the relaxed problem. In a sense, the actions that are in these policies here represent us working towards one of our relaxed objectives. So if a given action in our original model isn't present in any of these deterministic policies, it's not really working towards any of our relaxed objectives, so we are going to ignore them even when calculating the time-bounded objective. Of course, it will be suboptimal, but we'll also reduce the branching factor by quite a lot. So yeah, that's what I have here. For the product, we look at all these transitions, all these policies. If there is a certain transition that doesn't appear in any of these policies, we just take it out. And then on this pruned product, we add the time component, and we'll solve our original objectives in this simplified model with the time component. So going back to the diagram, this is what we had before. Now this is what we had to reach Pareto fronts for time-bounded objectives. So as I told you, we prune out the transitions according to the expected time Pareto front. We obtained a prune model. This prune model, we add the timing information, and in this product MDP, which is pruned and has timing information, we generate the Pareto front. How does this look like in terms of results? So this is the results for the optimal case. These are the Pareto fronts we obtain for our approach. So a couple of things. As I was telling, we go from solving a problem in a model in the order of millions of states to solving two problems with some hundreds of thousands of states, a sequence of two problems, and we can increase the speed we do it also. Second of all, we are still providing probabilistic guarantees over the policies we are generating. We are providing, even though they are not optimal, we are providing exact probabilistic guarantees over the performance of our policies here. And then we also analyze, of course, we are slightly suboptimal. You'll notice that we are less suboptimal in the area we are interested in, which is good. And also, so we compared, in order to kind of have a measure of our suboptimality, we compared the policy that you would obtain by having kind of 99% of the best possible probability of achieving the formula in the optimal policy. We compared the reward we would obtain there with the reward we obtain by imposing the same exact probability on the policy obtained from the prune model, and we compare how much reward that is. And you'll see in the worst case, in this specific example, we're doing kind of 73% optimal, but in many cases we're doing much more. And yeah, just to highlight that, we have quite a substantial reduction in terms of our number of states. Okay, just to wrap up, so I presented an approach that allows for the integration of kind of spare time observational planning with task-driven planning while still providing probabilistic guarantees over the performance of your system. And of course, integrating these two is much better than just trying to do the two things in sequence, as I guess is more or less obvious. Our approach is based on multi-objective model checking techniques. So again, we are really very interested in being able to provide these guarantees of performance, which can be used for other scheduling approaches that are working on top. For execution monitoring, there is a lot of ways these guarantees with the real world meaning can be used afterwards. And we presented the pruning operation that really reduces the state space of our problem and does not lose much optimality. Take this with a slight grain of salt. So future work. We have been generating this very rich set of Pareto optimal policies, but we don't have kind of a well-defined way of choosing a specific one for a given point. So what I showed you before was choosing one which is 99% optimal, but is that really, so looking into a specific case and having a nice way to pick from that Pareto front what is a policy that you really want is something that we want to look at. We don't have this implemented on the real robot at the moment, so we have other work on policy generation, which this work is building upon, but where we don't really take time-bounded properties into account, so that those policies have been executed in these long-term deployments for several months, and they are quite robust. Here we have to count time while executing the policy, and that's something that we haven't had the time to do yet, but we're doing it soon. And this is still not online, as I guess you noticed. We're still taking in the order of 20 minutes to calculate the policy. I think if we start using some probabilistic planning and MDP heuristic search techniques, we can make this faster, and we also are working on integrating this kind of technique into our approach. And that's it. Thank you very much.
My question, I guess, is about how confident you are that that would work in practice in real scenarios, because relying on full policy for real scenario, it's quite complicated, right? You still have a lot of stage to explore. So
yeah, if you want to finish, okay. So this model I showed you here is already quite complete. So we have a very coarse discretization of the environment in terms of navigation, but we do have a lot of data that we gather throughout our deployments to have nice statistics over how long it takes. Which means that our models grow, and as you saw here, they grow quite a bit, but they don't grow as much that we cannot solve them. So we have been executing policies in the real world which are not time-bounded, and these ones we cannot do them online, which is a bit of a limitation. We have to pre-process everything before, but we are able to solve for environments which have, let's say, in terms of the size of the topological map, on the order of high tens of nodes, close to 100, we can use this technique. So I would say that it is usable, and of course it's still not fast enough. We want to do better, but another problem that I see in terms of putting this in practice is this discretization of the expected duration that we're doing. Then we'll have to kind of fit the real time that passed with the right cluster representative, and there we have some kind of issue with timing. So that's something that I'm a bit less confident about. In terms of scalability, I think we can do something here.
So in a real application, once you have your Pareto front, how do you choose?
Exactly. So that's one of the features. Where currently what we're doing is really saying just hitting 99% of the best we could do in terms of the primary task, and taking that probabilistic policy out and executing it, which is quite a naive approach. So we want to really look into a better way to kind of maybe use some kind of the slope of this Pareto curve to figure out where we want to stop going up and where we want to stop sacrificing the primary goal. But it's still not very clear. So if you have some idea to it.
So why not considering the probabilistic objective as a constraint?
Because then we cannot really analyze the Pareto curve and see how the Pareto curve goes up as we sacrifice one of the objectives. That's the main thing. So by building the Pareto curve, you have really a high-level view of how the trade-off is done. If you put it as a constraint, you lose that ability, because you already, at design time, you have to say what's the bound you have.
Sure. So it means that you will have an operator that will choose the policy ultimately before execution.
In the case you're saying, that's what would happen in a sense.
Okay, any more questions? If not, let's thank Bruno again.
Thank you.